Hi everyone, this is Professor Mayunger and you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show the fourth video of this coursework. It is a cantilever beam with concentrated load at two different points, right? Let us see the statement of the problem. Using ANSYS mechanical APDL, draw the SFD and BMD of a cantilever beam of span 1.5 meter, carrying a point load as shown in figure, and compare the results, right? So the problem is, it is having a cantilever beam of length 1.5 meter, and we are providing a point load of 2 kilonewton at a distance of 1 meter from left hand side, and another one of 1.5 kilonewton at a distance of 1.5 meter. That is from origin at a distance of 1 meter and 1.5 meter. We are providing two concentrated loads. We need to find the shear force and bending moment diagram of this beam, right? So without wasting time, let us start analysis using ANSYS mechanical APDL. Okay. First of all, we need to create a directory and everything to be saved in that directory. Next to that, we can change the title of this one. Let us change the title from here, and we're keeping the name of this one as FEA4. Okay. To see the title, can click plot replot. It will show the title at the lower left corner. It is visible right now, right? Next to that, we need to select what type of analysis it is. It is a static structural analysis, and it will come from preferences. Preferences, structural analysis checked in. Okay. Next to that, we need to provide elemental properties, and that will come from preprocessor. Element type, add, edit, delete. Let us add it, and it will be beam 3D final strain with element type reference number is 1. Okay. Now from options, you can select element behavior as QV form. Okay. Let us close it. Now we need to provide material properties, and we know that it will be having modulus of elasticity of 2 into 10 to the 11 Newton per meter square and Poisson's ratio 0.3, right? So material models, structural, linear, elastic, and isotropic. Isotropic means material property remains same in all directions, and modulus of elasticity is 2E11 and Poisson's ratio is 0.3. Okay, done. Now we need to provide sections. So sections, beam, common sections, and as usual, it will be a square cross section of breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. Now we need to start modeling. Create key points in active coordinate systems. Let us see the drawing again. Beam is having length of 1.5 meter. We need to create 3 defined key points. First key point will be created at origin, so apply. It is done. Next one will be created at a distance of 1 meter from origin. X equal to 1, apply. Second key point is also made. Now third one will be at a distance of 1.5 meter from origin, right? X equal to 1.5, apply. We created all the 3 different key points, and another key point will be put for the orientation of this beam. Let us point that orientation key point as at a distance of x equal to 0 and y equal to -1. Okay, all the key points are made. Now we need to combine all these points in the form of lines. So lines, straight lines, you can select key point 1 and 2. Now the next one, 2 and 3, join together. Okay, now we need to start meshing. So meshing, and first of all you need to select mesh attributes, and you can select all the lines because we need to consider that orientation point also. So we are selecting the orientation point from here. Okay, let us pick that orientation key point from here. Okay, it is done. Now we need to start meshing from size controls, lines, all lines, and we are keeping the elemental division as 10 for each of the lines. Okay, done. Now finally we can mesh it. Mesh, lines, pick all. Meshing is done. Now we need to apply our boundary conditions from here, loads, and analysis type. It is a new analysis, and we are performing static structural analysis. Okay, done. Now we can define loads from here. It is a simply supported beam, right? So by structural displacement on key points, let us select key point 1. Okay, we are keeping all degrees of freedom with 0 displacement, so it is restricted to move in all directions. Okay, done. First boundary conditions are applied. Now we need to apply other concentrated loads. For that we need to see the lines again. Plot lines. We need to apply two defined loads at this location also and this location, right? Let us see the loading. At location C, we need to apply a load of 2 kilonewton, and at B, we need to apply a load of 1.5 kilonewton, right? So apply structural force moment on key points. Let us select first one. Here we need to apply a load of 2 kilonewton, right? Apply, and it will be in the direction of Y, and as it is in the downward direction, it will be minus 2000 newton or 2 kilonewton applied. Now the last one at extreme right hand side selected, and it will be 1.5 kilonewton in the Y direction downward, so it will be minus 1500 newton. Okay, done. We applied all the boundary conditions. Now we can solve it. So solution: solve quantiles. If everything is right, it will show solution is done. Okay, solution is done, so everything is perfect. We can see our results from general post processing. Let us close it. General post processing. First of all, we need to read results, and you can select the last set. Now we need to define the element table. Define table, and as usual, we need to specify some numbers for shear force and bending moment. So let us add it. From drop down menu, we need to select by sequence number and SMISC 2 for bending moment. Apply. Repeat the process again. By sequence number and SMISC, it will be 15. These two numbers, 2 and 15, for bending moment. Applied. Next one, we need to select numbers for shear force. So repeating the process by sequence number and SMISC, it will be 5. Apply. Finally, the last one, by sequence number and SMISC, it will be 18. Okay, done. We have selected all the numbers. SMIS 2 and 15 for bending moment, and 5 and 18 for shear force. Just let us close it. First of all, we'll see the result for listing, and we want to see reaction solution. All items you can see here, it is 3.5 kilonewton in the Y direction, right? And next to that, we want to see our results in the form of listing. That means we want to see the shear force and bending moment together in the form of numbers. That will come from element table data, and you can select all the numbers. SMS 2, 15 for bending moment, 5 and 18 for shear force. Okay, done. These are all the results for shear force and bending moment. Let us see in a better way. First two columns are actually for bending moment, SMS 2 and SMS 15, and third and fourth is for shear force. You can see the numbers. First one is here, it is for bending moment. You can see here maximum bending moment and minimum both are in the negative direction. It is ranging from 4.2 kilonewton meter to 75 newton meter, right? And also you can see here shear force. Maximum shear force is occurring at node number 1. It is 3500 newton or 3.5 kilonewton, and minimum is 1500 newton or 1.5 kilonewton. Okay, let us close this one. Now I want to see the results in the form of graph, so we need to plot it. Plot results. Can do plot line elemental response, and we want to see bending moment, so it will be SMS 2 and SMS 15. Okay, let us see this one. It is in the negative direction. You can see minimum is minus 0.58 into 10 to the minus 6. It is approximately 0 here itself, and you can see the maximum negative value is actually 0.4250 kilonewton meter, right? Let us compare the results with the actual answer from the question paper itself, right? Let's see, minimum bending moment is 4.25 kilonewton meter. Next to that, we want to see the shear force diagram, line elemental response, and we can change the numbers. It will be 5 and 18. Okay, this is the shear force diagram. We can say maximum shear force is starting at origin, it is 3.5 kilonewton, and minimum is also extreme right hand side, it is 1.5 kilonewton. Let us see the drawing of the question to compare this one, right? It's showing that maximum is at the origin, it is 3.5 kilonewton. It is ranging from A to C, and minimum is ranging from C to B. Minimum is 1.5 kilonewton. It is exactly same what you saw in our question paper. So our question paper is validated with the answer obtained from ANSYS mechanical APDL, right? Next to that, we'll see the animation of this one. So first of all, you need to see the model in 3D. Plot controls, style, size and shape, and display of elements should be on. Let's make it on. Let us see the element, plot element. So this is the model. We can see in a better way from oblique view. So this is the model. You can see this is the model with a specific cross section of 0.01 meter by 0.01 meter. Okay, now we'll see the animation of this one from plot controls, animate, deform results, and by default setup we can see the translation along y direction. Okay, let us see the displacement of this cantilever beam. I can change the delay period to see this one in a better way. So this way it will be vibrating, right? Let us close this one. With this one we will conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.